Hi, I'm Michael Gleischer, and I'm going to talk about some work that I've done with my former students, Xinyi Yu and Yuhong Chen. The paper is entitled Trinary Tools for Continuously Valued Binary Classifiers. This work talks about how we can build support for machine learning practitioners and how they work with continuously valued binary classifiers. Our work considers three phases of tasks. It presents designs for supporting these tasks, and it integrates these designs into a system that supports the various workflows that we saw people needing to do. Our work has been embodied in the CBoxer system. The system is open source and web deployed, and you can go to the link that I'll give you at the end and try it out. So I could talk about this as a systems project and show you the system that we built. It's very much based on our prior Boxer system. I could talk about the focus of the paper, which was the specific techniques that we added to the system in order to better support continuously valued classifiers. Because this is a workshop talk, I was hoping that I could spend some time giving some discussion-provoking thoughts about some things that we've encountered and learned over the process of building the system. Now, to give you a sense of where CBoxer sort of fits into this machine learning workflow, we consider cases where a practitioner has built a classifier or is in the process of building a classifier, and they take test data, they process the test data to get results, and then they need to look at those results to assess how well their classifier is doing. Now, notice that this is going to treat the classifier as a black box. CBoxer takes as inputs the test data and the classifier results and looks at these two things together. Now, a binary classifier makes a yes-no decision. A continuously valued binary classifier also makes a yes-no decision, but instead of just returning yes or no, it returns a score. I'm going to, without loss of generality, say that that score goes from a minimum value of 0 to the maximum value of 1. Now, ultimately, this score translates to some binary yes-no kind of a thing for some threshold. However, the score, if it's higher, hopefully means it's more likely to be positive, and if it's very low, it's more likely to be no. Now, of course, that correspondence between the score and the probability of knowing the answer requires the classifier to be calibrated. That term calibrated means that the scores actually match the probabilities, that the scores have meaning. Now, in an ideal world, the scores do have meaning. The scores would directly correlate to probability. Now, in the real world of machine learning, the scores may not actually directly correspond to probabilities. There could be some random factors involved. It could be that they're poorly tuned, so a classifier is over or underconfident. It could be that the numbers just are yes or no. Therefore, when you have a classifier, you must assess the calibration empirically. That means we need to check on actual examples to see how well the classifier does and do the scores actually correspond to probabilities. Now, if the scores do have meaning, we can use them to make a three-way decision. If we're very confident, we could choose yes or no. But if our confidence is not so high, if it's sort of in the middle and it could go either way, we could decide that we're not confident enough to make a decision. In machine learning terminology, this is called rejection, because we're going to reject the opportunity to make a decision. It's basically saying no decision. So in using a classifier, there's this notion of setting the threshold of where we're going to make choices. Thresholds are sometimes called operating points. We can choose an upper threshold, of which if the score exceeds the upper threshold, we say yes. We could set a lower threshold. Things below that we say no. And then we have an in-between band. We could also view this as a single threshold and a width of the band in between things. Now, this idea of trinary, of yes, no, and reject or no choice, is important because, well, sometimes the goal with a continuous valued classifier is to build a trinary classifier. And sometimes we're going to keep the continuous score as a probability, but we'd like to be able to use the trinary characterization as a way to make decisions and group things together so we can do subsequent analysis. Now, our prior work, we built a system called Boxer, which focused on discrete choice, not continuous classifiers. It was an interactive system that allowed for comparing the results of these kinds of experiments. It just looked at inputs and outputs, and it built up these flexible coordination mechanisms where you take different views, put them together, and connect them via selection. So the simple story for this paper might be to say, well, all of our collaborators actually wanted to deal with continuous problems. They didn't want our discrete system, so we had to extend our system to handle the continuous data. The interesting parts of this is we saw a multi-phase workflow where we had to deal with these problems of calibration, threshold selection, and other examinations of the continuous data. We needed to enhance our ability to select groups and identify individuals, and we needed to provide support for practitioners who had some very specific ideas about which particular ways they like to look at this kind of data. So one of the big ideas that we sort of took away from this is that if we're going to build a system to support these processes, we needed to provide support for all phases of working with classification. We had to deal with calibration and threshold tuning, in addition to the more traditional examination and assessment tasks. Now, assessing calibration is something that is a standard problem, and there's very standard practice. There's a standard view called a reliability or calibration curve. We built this into our system in what we call the reliability curve view. We extended it in some ways that highlight the sort of our philosophy. It's specifically designed to support comparison so we can look at different classifiers. It's a multi-view view because it not only shows what the curves are, but it also shows us the amount of elements at each level. So we can see there aren't very many of these 0.1s, and that probably explains for the high variance, the high variance there. Another aspect of this is this view is tightly integrated into our system. That makes it easy to do calibration, which means that you won't just skip it and say, oh yeah, I'm sure that I just trust that the classifier is calibrated. It also means that we use the selections. You can actually click on these little bars to select those items, and that makes connections to other views. Now, we have a slightly less standard thing called a confidence view, which shows the various scores on the vertical axis. For each score, it's a histogram that shows how many items have that score. And for each one of those shows how many is correct in blue and how many are incorrect, that's the pink. This requires us to have the thresholds. In fact, you can see the no decisions because this is the dual thresholds. And it gives a very broad view of where the errors are and what the distribution that the classifier is providing. But in order to show the errors, it has to have the threshold set, which of course says, well, what do we do about setting the thresholds? The standard practice that our collaborators use is they would use the standard curves, ROC, receiver operating characteristic curves, or precision recall curves. Different people have different reasons why they prefer one over the other. They looked at these plots and chose the ideal points on the curve. So what do we do for thresholding? We provide those standard curves. We also allow for experimentation. We give interactive controls with sliders that allow the user to explore different values and see how they cause trade-offs in terms of various performance metrics. We also provide some specialized views that were specifically designed to support the threshold setting task. So I'll run through these. The first one is a rejection curve, which is a somewhat standard view. It's often used by machine learning practitioners. It allows us to view how, as we raise the rejection rate setting the thresholds to be farther apart so we reject more items, we can improve how the performance changes. This is useful. It assumes that we can set the single ideal threshold. A second view that we built deals with the problem of that previous view, that it requires picking a single center threshold first. We built what we call the bandwidth assessment view that allows us to look at several different thresholds. It allows us to look at 3 different bandwidths. You can see 3 different levels here, and 3 different levels for everything in between. And lets us see how many items are rejected and what the performance is for across all of those different ranges of things. Now, this view packs in a ton of information and it's not very easy to use. So we tried something else. Another experiment we've tried was to use what we call the uncertainty heat map. We take all pairs of threshold, the lower bound and the upper bound, and for each one of those, we need to know how many items are rejected and what the performance is. So we have to show 2 numbers. We map one to color and one to size. So here we can see, say, down here, we get pretty good performance, that's the orange, but without rejecting very many. The circles are big. Whereas up here, we get better performance, more yellow, but it rejects a lot of things. The circle is small. Now, these novel task-specific views have upsides and downsides. The good news is they provide needed information and they support different preferences. At different times, we like different ones. It allows us to choose which one is appropriate for a given task. However, it does mean we have to have the users learn how to use all these different views. We need to be able to spend time choosing which view. Just because you have them all, you don't necessarily know which one is the right one to use. Now, for examining classifiers, we can use various views provided by the systems to see the aggregate statistics. In those views, we can use those to select groups. We can combine groupings to refine things. And then we can examine individuals within those groups. These are all mechanisms that were in the original Boxer. But to give you a quick example, here, I'm using a view that shows me how many items for each of 3 different classifiers. Here I've selected by picking it. It shows up in cyan the rejected items for this particular classifier, and I can see where they show up in another view that's showing me one of the particular classes. So one of the interesting things I can see from this is that for sex equals 1, which are females in this case, the number of rejected, the rejection rate is much higher than for males. Now, the system itself uses selection mechanisms to tie together views and provides a wide range of views. The original Boxer system had a whole bunch, and we've added a whole bunch more. Do we really need so many views? Now, my answer is maybe, because experts tend to want their favorites. We need views that are adapted to specific situations. Some of the views do have very special purposes. And some of the views are there to support selection and control, so they magnify the utility of other views. And if you really look at it, there's really a few simple configurable views that do most of the heavy lifting in the system. Ultimately, we have to have this because users demand flexibility. But there are downsides. Users need to learn about these views. They have to be able to make choices about which views to use. They have to know how to coordinate the views. They need guidance and training, which is something we've been working on in the system to build good user guidance and training support to make this all possible. But I think one of the big lessons here is that the flexibility is hard to add without bringing in additional complexity. So, to sum up, in the paper, we talk about a system for examining continuously valued classifiers. It considers 3 phases of tasks. It provides some specialized design. It shows how all these work together with coordination mechanisms, and shows how we can use discretization to do grouping that helps us organize our data to be more useful. For discussion, I think it's interesting to think about how all of these flexible mechanisms that are required to support expert users who do machine learning work, how do we build a system that provides that flexibility without having too much complexity? And you can try the system out for yourself. So I will conclude by giving you a link so you can try it out and thanking my sponsors and thanking you for your attention.